Hi guys, welcome to another video by TechSense.
With the launch of the James Webb Space Telescope, there was a lot of talk about how it is not serviceable manually since it's too far away from the Earth at the point called L2. What's this L2 point?
Okay, L2 point is what is known as a Lagrange point. Lagrange points are reputed as the parking spots of space. At those points, the gravitational pull of two large masses like the Sun and the Earth precisely equals the centripetal force required for a small object to move with those two large masses. Therefore, spacecrafts can use them to reduce fuel consumption needed to remain in position.
Yes, there are 5 of these points which are named after the renowned mathematician Joseph Louis Lagrange. The first 3 points L1, L2 and L3, which lie along the line connecting the two large masses, were actually calculated by the mathematician Leonhard Euler. These 3 points are unstable because the small object will continue to move further away, even if it's slightly off from the point.
The other 2 points, L4 and L5, which form the apex of two equilateral triangles that have the large masses at their vertices, were computed by Lagrange in his 1772 paper named this. I'm not going to pronounce it for obvious reasons.
Tris, it's good. Holy cow, that's a big word. Tris,
In the paper, he considered the mathematical problem known as the general three-body problem to calculate L4 and L5. As long as the mass ratio between the two large masses exceeds 24.96, which is satisfied by both the Earth-Sun and the Earth-Moon systems, these two Lagrange points are stable, since the orbit of the small object will only shift marginally if it's slightly off from the point.
The L1 point of the Earth-Sun system has an uninterrupted view of the Sun and is currently home to the solar and heliospheric observatory satellite SOHO.
The L2 point of the Earth-Sun system was the home to the WMAP and Planck, current home of JWST and future home of Plato.
Now, let's calculate the distance from the Earth to L2, considering this as a restricted three-body problem where the Sun is stationary, since the center of mass of the Sun and the Earth is located deep inside the Sun.
Let's define some terms. G as the gravitational constant, T as the period of the Earth around the Sun, ms as the mass of the Sun, me as the mass of the Earth, m0 as the mass of the small object, r as the distance from the Sun to the Earth, L2 as the distance from the Earth to L2 point. Assuming m0 is at L2, let's apply F equals ma to it towards the Sun. Gravitational forces by the Sun and the Earth on m0 should be equal to m0 times the centripetal acceleration of m0. Next, let's define simple a as the centripetal acceleration of m0. Then, we get this equation and let's refer to it as capital A. We can get another equation for a with omega, the angular velocity of m0. Since the Earth and m0 move together around the Sun, their angular velocities are equal. Therefore, their periods around the Sun are equal. Now, we have two equations for a. This will give us a fifth degree equation of L2, which is inconvenient. However, since we know the values g, ms, me, r and t, we can plot left hand side and right hand side equations in the same a versus L2 plot and find the intersection. Or, one could use Wolfram Mathematica. You can use this Python script to plot. We will put a link to this in the description. It will generate this graph. One can see that L2 is approximately 1.5 million kilometers.
Now, you can try to modify the final equation and the Python script little and calculate L1. You may get a graph like this.
Comment below what changes you made.
Okay, now you guys know what the L2 point is and how to calculate the distance to it from the Earth. If you enjoyed this tech step, please like and share. If you have any suggestion, feedback or question, don't hesitate to comment.
We are planning to bring you more useful content from different tech fields in the future. So, to stay tuned, please subscribe and hit the bell icon. See you soon.